Well, hi, this is Luke Pinkerton. First, I want to thank you for choosing to participate in this continuing education course on global warming in the concrete industry. This course provides one AIA LU/HWH CE hour and one RCEP PDH hour for engineers. As I said, my name is Luke Pinkerton. I'm the president and founder of Helix Steel. My background is structural engineering I graduated from the University of Michigan, and I've got about 20 years of experience in the concrete industry, primarily working with Helix, the Helix Steel company and the micro rebar product. I also want to thank Zubair Akhtar who is actually a junior at the University of Michigan who helped prepare this presentation as part of an internship. So we're going to go ahead and dive into this presentation. A little bit of housekeeping to get started. As I mentioned, credit is earned upon completion of this course for AIA. Certificates of completion for both AIA and non-AIA members are available upon request. This course is registered with AIA CES for continuing professional education. As such, it does not include content that may be deemed or construed to be approved or endorsed by AIA of any of the material or methods, manner of handling, using, distributing, or dealing in any product or material. You will receive an automated quiz after this course. If you score 80 or above, you will get a certificate. If you have issues with that, go ahead and reach out to us and we'll make sure we get that taken care of for you. The course is also meets the standards for the registered continuing education program through RCEP. Credit is earned upon completion of the course. We will report completion after you complete the quiz to rcep.net, and those certificates are issued directly from that system. So please make sure the email you registered for this is the one that you want us to send that certificate through to. So the description of the course today is here. The course is going to provide insight on how global warming is impacting the concrete industry. The capabilities of current metrics to assess global warming will be discussed, as well as essential tenets of sustainable construction and the frameworks used to assess carbon footprints. This course offers a study of material life cycle assessments, energy use, as well as best practices and procedural benchmarks to analyze and refine findings pertinent to industrial ecology. Finally, strategies for minimizing global warming impact will be introduced and solutions will be analyzed. The course is intended for industry practitioners, design professionals, and experts interested in promoting or pursuing sustainable engineering and construction principles, as well as anyone learning about how building practices are increasingly moving towards becoming environmental friendly. This course also provides knowledge about industry expectations and future trends in the industry. Here are our learning objectives. We're going to understand and communicate the internal external factors driving sustainable construction practices and what sustainability means to the industry. We're going to identify and assess key metrics used to study global warming and its impact on the concrete industry. Communicate the role of carbon footprint that use concrete, as well as energy costs and material life cycles in contributing to overall emissions, and how sustainable practices can reduce emissions and streamline life and use cycles. And finally, describe and critique solutions and strategies minimizing emissions and global warming, and how to best integrate those practices. So we're going to start with an introduction to kind of the situation with global warming. Global warming is something that's been talked about a lot over the last, really my entire lifetime. I remember those first kind of back in the 1980s, Earth Day becoming more and more important and talked about. Back then we were talking about CFCs and the ozone a lot, but certainly what they have found is that the carbon dioxide in the atmosphere is really the main culprit. What happens is, as we burn fossil fuels generally, that carbon dioxide is released into the atmosphere and it collects in the atmosphere, and the CO2 prevents the heat from the excess heat in our environment from being radiated into space. Instead, it's just bounced back and held within Earth, within our atmosphere, similar to how a greenhouse traps heat if you're trying to grow plants. Carbon dioxide is considered a greenhouse gas because it does have that property. It prevents the heat from escaping. Methane is another gas that has a significant impact. But carbon dioxide in particular is something that is very quantifiable. There's a very real increase in it. You can see this data here that's actually from NASA that shows the amount of carbon dioxide in our atmosphere over the last 800,000 years. And you can see there's kind of a cyclic nature to it. This is actually very scientifically determined through extracting cores of ice, and they can look at the gases that are trapped in the ice, and they can determine based on how deep the ice is, how old it is. So you got these very accurate measures of carbon dioxide in the environment, and they're kind of cyclical until we get up to around, that industrial revolution period, 1800s, 1900s, it just starts to skyrocket. And that's likely because of all the fossil fuel burning that occurs here, as well as in other countries where, there's just a lot of demand for higher standards of living that require more energy. And the go-to method for energy, at least the last 100 years, has been burning fossil fuels, which creates that CO2. So how does that relate to the concrete industry? Concrete is not particularly, concrete is a material that we'll talk about that has many component materials, but the one material that does have a relatively significant impact is the cement that's used in the concrete. And the cement has a relatively high carbon load in terms of the amount of carbon that's produced when it is manufactured. That comes from the burning. It requires a lot of heat to make the cement. So there's fossil fuels that are burned there, and then the reaction that occurs when the cement is manufactured actually releases carbon dioxide. So that the material itself, cement, which actually only accounts for a small portion of the overall concrete, we'll talk about later, has a relatively high amount of carbon. But perhaps the bigger thing that's involved here is that concrete is the most widely used artificial material in existence. So there is a lot of concrete being used in the world, more than any other artificial material. So just the sheer volume of concrete being used, regardless of the facts about the cement that's within the concrete, makes it a major contributor. So, many of the world's associations that are affiliated with concrete, like the Portland Cement Association here in the United States, have recognized this and have taken very proactive steps to curb this. Obviously, we need concrete. It's in many ways, and I'll talk about it's a very good material to use. It's available in places that more, I guess, exotic materials just can't be used. And there are many advantages to using it. And what the Portland Cement Association is driving towards is complete carbon neutrality by 2050. So that's a really ambitious goal. It means that we're going to need to innovate in terms of how we build with concrete. It's also going to mean that we need to innovate with the materials. So, there are quite a bit of sort of misconceptions, and we'll talk about this on the next couple slides. You have books like this one that was published by Bill Gates that has a whole chapter that's devoted to concrete and building materials, and it kind of goes over the situation and kind of recognizes some of the things that I talked about earlier and challenges the industry to really innovate around how we build. So the PCA is actually was answering this even before the book was published, but I think as industry professionals, we need to always be looking for ways to be a more efficient and more conscious of the impact that the way that we build has on the environment. And that's really what Bill Gates was saying in here. A lot of people would say that he's sort of bashing the concrete industry, but I think really what he was saying in the book was more of a challenge to innovate. So, I think we need to look at it holistically, and we're going to talk about how you can kind of put this in perspective in the next couple of slides. There's no doubt that building materials, especially when you build a building, provide quite a bit of carbon emission. But there's also a life cycle. How does it affect? How is that building that you build going to contribute over the life cycle of its use and eventual recycling or reclamation of materials? So there are things that we have to look at. We got to look at the big picture. I definitely agree. We need to be looking at how we can become carbon neutral with cement. And there's some really cool technologies out there that can help us with that. But, I think really we should focus on innovation as opposed to, moving to different forms of or types of materials that, might not be as practical or have as many benefits as concrete. So if you're watching this, you're probably involved in concrete construction, but if we focus on some of the benefits of concrete construction from a sustainability perspective, really the biggest thing that cannot be ignored is the service life or the long life of concrete. Pavements, generally concrete pavements last longer than asphalt pavements, for example. Homes and buildings that are built with concrete last longer than buildings that are made with other materials. Further, when you use concrete, you can reduce, in particular, the amount of energy that's needed to operate a building. Insulated concrete form construction, for example, uses concrete along with foam insulation and provides a very, very tight seal of the envelope of the building, which makes the energy cost to operate a building very, very low. And this table here was actually published through the NRMCA and MIT by Tian Peng a few years ago. And it really shows, if you look at the green at the bottom, what it's doing is comparing the upfront cost of construction in terms of carbon footprint or global warming potential to the 60-year lifespan impact. And you can see that red part of the curve is the impact after construction, and the green part is before construction. So yes, there's a slight premium to using concrete in the construction phase, but over the life cycle, compared to other systems like wood, you actually have a lower impact because you've got better environmental performance, less energy demand on that building that has that tighter envelope. And that applies both in a hot climate like Phoenix and a cold climate like Chicago. And it's universal also to single family and multifamily. So the NRMCA has quite a bit of information like that on their website, as well as the Build with Strength website. The other benefits to concrete are things like safety and reliability and resilience. Obviously, this ties into climate change as well. More severe weather incidents really we have to pause a little bit before we build a building that is maybe light stick framed in a hurricane prone area versus, say, an insulated concrete form home that is going to exhibit more resilience in the face of a category 4, category 5 hurricane or tornadoes and things like that. So we can actually, with concrete, we can design buildings to actually be serviceable through that type of event, not just something that doesn't blow over, but something that remains completely usable. And we've seen that in some of the projects that I've been involved with in the islands. In particular, we had a project in St. Martin that was built with ICF that was exposed to Hurricane Irma and sustained almost no damage other than a few sort of aesthetic damage to the building. There was no structural damage, and the building remained completely occupiable and serviceable through the storm and after the storm. So as I said, the NRMCA's Build with Strength campaign has a lot of great information on that. So now we're going to dive into evaluation methods and metrics that are related to environmental impact, rather. And the three things that we're really going to focus on today are what's called product category rules, PCRs, LCAs, which are life cycle assessments, and EPDs. And these are the things that you really need to be familiar with as we kind of get into this regime of quantifying environmental performance of building products and building systems. So this is kind of the hierarchy here. We're going to go through all these in a little bit of detail, but it all starts with a product category rule. And this sort of is your high level definitions of how you are to assess things, what the system boundaries are and things like that. The life cycle assessment is where you get into the details of a particular product, for example, something like rebar, for example, where a third party or a practitioner, independent practitioner, will develop data based on the rules that are in the PCR to quantify the environmental impact. And then the EPD is more of a executive summary that presents the outcome of the LCA in a way that's easy to digest. So we're going to kind of go through each of these. The product category rule is the foundation of the EPD. It contains system boundaries, which you can see kind of here. This is a common sort of system boundary regime. You have a production stage, you have a construction process stage, a use stage, and then an end of life stage, which actually considers, in the case of building, tearing down the building and maybe recycling some of the components. So it includes the system boundaries. This is the example here, declared functional units. And that's really important. And that can be really confusing for us here in the United States because we're still stuck on the imperial units. Generally, the carbon footprint or really all the EPD values that we're talking about, and I'll show you what those look like in a minute, are reported in metric units and universally. Whether your inputs are imperial or not, the output is always going to be in kilograms of CO2 into the atmosphere, for example, for global warming potential. It also has definitions in different categories. You can't produce quantified data on environmental performance without a PCR. And you really got to be careful if somebody is presenting something to you that doesn't reference a PCR, because you just don't know what the rules are. And certain liberties could be taken that maybe don't fall into the category. So groups like NSF and ASTM publish these PCRs. You can find them on their websites. This is an example of NSF's PCR for concrete. So once you have the PCR, that kind of assigns the system boundaries, the rules, and high level kind of regime by which you're going to evaluate a product. You can work with an independent group or an independent consultant usually to develop what's called a life cycle assessment, or LCA for short. And what this does is it really analyzes the contribution of the various life cycle stages to the environmental load, usually with the aim to prioritize improvements on products and processes. It uses the system boundaries that are defined by the PCA, but it may not include the entire life cycle. A lot of products, for example, stop at what's called a cradle to gate analysis because, for example, the rebar really, a rebar provider can't really say anything about what's going to happen after the rebar is installed. They can provide a quantification of the life cycle impact up to the point it's delivered, but after that, it's kind of it goes into the hands of the building owner to complete that analysis. So this is kind of this diagram kind of shows all the different things that go into this. It starts with really the raw material, and you look at how much energy, how much carbon is produced by the raw material acquisition, then the manufacturing process, and this takes those raw materials and converts it. So there's usually energy that goes into this. There might be chemical processes that produce carbon or other photochemical smog producing agents and things like that are evaluated in EPDs. Then it actually looks at transportation, and transportation is actually a big issue. And if you look at all in the news now, how difficult it is to move things around, the big container ships, issues like we saw with the Suez Canal and a ship getting stuck in it. There's a lot of carbon that comes out of those ships, and we're shipping things all over the world in these containers. And I will say it's not an insignificant amount of carbon load that occurs from distribution. And then its use. So in the case of concrete, that would be actually installing the concrete and or like reinforcement. And then you get into sort of what happens at the end of the life cycle. Do you reuse the materials? So like, for example, with concrete, a lot of times they will crush the concrete. The concrete is used as aggregate sometimes, or it's used as stone base and things like that. So you go into a reuse. The rebar is often reused. Some other building materials are not as easily recyclable. They might be disposed, and that has certainly a higher impact because it can't go back into a use stage. And then could there be recycling, for example? So the LCA looks at all these things sort of holistically based on the system boundaries that the group that's asking for the LCA defines, and then they produce an assessment. The assessment is done in these sort of 4 steps. As I mentioned, the scope and the goal, the inventory analysis, the impact assessment of all those areas we talked about, and then the interpretation of the results. And this is common. This is actually an LCA for steel rebar. And in this case, they just go through what's called the A1 through A3, which is raw material extraction and transport and fabrication of the steel. So this is how they define their boundaries for this LCA. And this is a cradle, what's called a cradle to gate performance for the analysis. So that's just, they're different terms for different life cycles. What this does is that in the course of this analysis, you're able to develop quantifiable data that shows the performance in terms of things like global warming impact and total energy consumption that goes into this product. And that data then is summarized in the EPD. And I'll show you some examples of what EPDs look like in a moment. The environmental, or I'm sorry, EPD, Environmental Product Declaration, is the kind of the final step in that summary that I talked about. So again, I'm not going to, we'll show some examples of this and it'll be a little bit more illustrative later. But this is sort of the executive summary of that LCA. And you can almost think of it as a nutrition label for the product. It'll have all the key metrics that are used in these assessments, like the global warming impact, which is the amount of CO2 that's released into the atmosphere, that then can be used by somebody else down the chain to quantify the overall impact of, say, an assembly or a building. There is a certification regime for this. There's an ASTM or an ISO standard for that. There are certain companies that certify these. They provide third-party certifications. Underwriters Laboratory is one, ASTM is another, NSF is another. There are quite a few companies that do it. It's similar to what would be needed for like a product evaluation report. It has to be a third-party accredited agency. All the data has to be third-party verified to be certified. Now you can estimate environmental quantities and values without that, but if somebody is asking you for an EPD as a contractual item, you would need to look for one that's certified and published through an organization like UL or ASTM. This is what an environmental product declaration, this is just an example, and I will show you some values from this in a little bit, but the National Ready Mix Concrete Association has prepared one for a wide variety of concrete mixes. So you can look at sort of the mix parameters and it'll give you the impact values for concrete based on those parameters. And this one's actually published and certified by NSF, which is one of the agencies that certifies it. The final thing I'll talk about a little bit, and this is related, but it's not specifically part of this PCR LCA EPD regime. It's the LEED certification process. LEED's been around for quite a while. And many of you are familiar with this certification system. There's also a LEED 0 system that's really driving towards carbon neutrality, energy neutrality, and then eliminating wastewater and waste in construction. So there's some new standards like this that kind of take it a step beyond the general LEED points. The reason I wanted to bring up LEED is that LEED 4.0 does specifically provide 2 points if you have one of these official EPD documents for the products that are used in construction. So you can get credit for just simply collecting these and having them when you are, if you're trying to reach some of these higher LEED certifications and you're looking for points. So I'm going to go over a couple common building materials as examples now, and then we'll show the EPDs for these, and then we'll talk about how we can kind of improve and optimize and baseline the environmental performance of these systems. So the materials we're going to talk about are steel and concrete, as well as twisted steel micro reinforcement. We kind of are pretty familiar with steel and concrete, and what we're really talking about is reinforced concrete, which has really been a very common method of construction over the last 100 years or so, where we use steel to make up for the weaknesses of concrete. Concrete's weak in tension but strong in compression. So basically, as the engineers will put rebar anywhere where the concrete goes into tension, where it tends to want to pull apart. And that way, when the concrete cracks, which it usually will do in a brittle manner, the rebar picks up that load after the concrete cracks. And it tends to work pretty well. The thermal coefficient of steel is similar to concrete, so you don't have issues with compatibility. The issues, of course, are, it's labor intensive, and you have corrosion and things like that. The other one we're going to talk about is an alternate building material called twisted steel, or alternate reinforcing material, which is called twisted steel micro rebar. These are small pieces that are mixed into the concrete to increase the energy absorption, durability, and performance of the concrete. So we're going to talk about first concrete and reinforced concrete. And this is something that's a little bit of a misconception if you're not familiar with the details of concrete. Some people mix up and call concrete cement. Cement is actually only 7 to 15% of the concrete. And the easiest way to explain what the cement is it's the glue that sort of adds, that sticks all the aggregate, which is sand and stone, together. So if you look at this little diagram here, the cement is up to about 15% of the concrete. So it's a relatively small percentage of it. Then you've got water, you've got air, and then you've got the sand and stone that make up the vast majority of it. So to kind of put that in perspective, typical cubic yard of concrete, there's about 10 cubic yards in a concrete truck, is about 3,900 pounds. And then when you install it with rebar, it becomes about 4,000 pounds per cubic yard. The cement in a cubic yard of concrete is usually between 500 and 600 pounds per cubic yard. So that's only, it's in that, 7 to 15% range. There are things that you can do to reduce it, but that's a general idea. The reinforcement or the rebar typically is about 5 pounds per cubic foot. So, that works out to about 150 pounds or so, 100 to 150 pounds per cubic yard. So even though steel has a very high impact in terms of carbon, similar to cement, it's just a smaller portion of what goes into that cubic yard of concrete. The cement is much higher. So that's why the concrete has the impact is really driven by that cement content. We're going to talk about twisted steel micro reinforcement a little bit more, as that may not be as familiar to you. This is a product that is shaped like a screw. It is twisted, and that twisted shape allows it to lock into the concrete and provide additional tensile strength that is not available excuse me, with rebar until the concrete cracks. The threaded shape locks it in and allows it to pick up the load even before visible cracks occur, which increases the amount of force that it takes to crack it. And then after the concrete cracks, it actually has to almost untwist to come out. So the behavior is driven by the twist and that untwisting failure mechanism versus just friction, which is what governs something that's straight or maybe has a discrete anchorage point like rebar. Or straight is what you would typically see in, say, fiber reinforced concrete products. The product itself is made of high tensile strength steel, similar to what you have in pre-stressing strands. It's about 1 inch long, 0.5 millimeter diameter. It's actually shaped like a rectangle and then twisted about its own axis. And it's relatively small. So there's about 11,500 parts per pound or 25,000 parts per kilogram, which gives a really good, it allows us to get quite a bit of performance and quite a bit of efficiency and consistency, even when it's applied at relatively low dosage. And dosage means the amount of pounds per cubic yard that you add to the concrete. So this is one of the most common things that's evaluated in concrete is compressive strength, and the twisted steel micro reinforcement actually increases that compressive strength, which is not something that typically is used for a performance benefit because concrete has such a high compressive strength to begin with, but it is something that more and more people are looking at. Are there ways to change the mix design so it doesn't need as much cement to reach a certain level of performance? And you can see here, just by adding very small amounts of twisted steel micro reinforcement into the concrete, you get increasing levels of compressive strength. So you could potentially decrease the amount of cement that you need in a particular mix by just adding this product, and the product would have a lower carbon footprint relative to the cement that you would remove. So that's one strategy that you can look at, and this can be done just by submitting a mix design that includes the product in it. The second property that is perhaps more important from a design perspective is what's called the modulus of rupture. So you can see here some samples of twisted steel micro reinforcement that were tested. You can see here that the flexural strength, and these beams are put in a machine that bend them until they break, actually it nearly doubles with the addition of the product here. This is a highly optimized mix design. In a more normal mix design, you're going to get a 6 to 15% increase at 9 pounds per cubic yard to 22 pounds per cubic yard of the twisted steel micro reinforcement. That's pretty significant given that plastic fibers or synthetic fibers really don't have any effect. If anything, they have a slight negative effect because they're actually softer than the concrete themselves. So if you can imagine it, they're like having rubber bands in the concrete. You have to stretch those rubber bands a little bit before they start to carry load. And in order to stretch them in concrete, because the concrete's not pliable, the concrete has to crack. So these products really are designed and looked at only after you have large cracks like you see here. Steel fibers can increase the modulus of rupture, but typically the dosage needs to be higher to do that because the anchorage isn't as good because they don't have that twisted shape. So there are other benefits to using a system like this because you've got distributed reinforcement throughout and you've got that very good bond. We talked about resilience earlier. This applies to things like hurricanes and tornadoes as well. Concrete just has a tendency to shatter around rebar. If you reduce the amount of rebar and you put twisted steel micro reinforcement in, you get a behavior that's entirely different. It's more what we call ductile, and you don't have the spalling that's here. So that's an added benefit of using an alternate material like this. Finally, to be able to use an alternate material like this, that if it's not specifically spelled out in the building code, you really need to follow the alternate material allowances in the IBC and the IRC. That's in section 104.11. We have another AIA RCEP accredited course that goes through alternate building materials and how those are used in industry. The TSMR has 2 evaluation reports, one through the ICC evaluation service, ESR 3949. You can download it from here, or ER 279 from IAPMO is another one. And these evaluation reports provide third-party assurance that the product meets the building code requirements, similar to how the EPDs provide third-party assurance that the quantities in them are accurate. They allow use of the TSMR product in things like ACI 318 applications, which would include footings, structural slabs, and walls, slabs on grade, pavements, and a variety of other applications that are in the IBC and the IRC 2009, 2012, 2015, 2018, as well as the upcoming 2021 version. They're published under ISO 17069, and they do have reciprocity about 99 countries because of mutual recognition arrangements that they have in these different areas. I'm going to give you a few examples of what the EPDs look like for these materials. So we're going to start with rebar. This is an EPD that is published for fabricated steel. I showed you the LCA for that earlier, but you can see here that these are the values that are published. These are typical. There's some other ones, but you can read through these. The ones that we're really going to focus on mainly is the global warming potential, which is your CO2 footprint, and the total non-renewable or total primary energy that's used in the construction. That's reported in joules, and the global warming potential is reported in kilograms of CO2 per kilogram of rebar. So for each kilogram of rebar, you basically are putting 1 kilogram of CO2 into the atmosphere. So it's almost a 1-to-1 ratio. For concrete, you saw this figure earlier. The nice thing about this this NRMCA EPD is you can look at your mix design if you're using fly ash, for example, or different supplemental or SCMs. There are different quantities here. So, for example, this one will represent a 3,000 psi mix with 20% fly ash, and then it just gives you a maximum and minimum value for your total energy and your global warming impact. So the maximum here is 257 kilograms per cubic yard, or cubic meter in this case, or actually this is per cubic yard. So for a cubic yard of concrete down here, 257. If you go to a 20% fly ash mix, which is fairly common in the industry, it's 220, which is what I reported here. They also have a table here per cubic meter, and because a cubic meter is a little bit bigger, that number becomes a little bit bigger. But keep in mind, even though we're reporting in English or imperial units for cubic yards here, this is still kilograms here. So that can be quite confusing, and just need to kind of get your units straight when you're doing that. So for twisted steel micro reinforcement, there is, I'd be very clear, there is not an official EPD published on it. However, the Athena Building Materials Institute has provided data, LCA data, for the product for twisted steel micro reinforcement. And that data has been used to develop the cradle to gate estimate for things like the values shown here. Again, the total primary energy is something that we're really going to be focusing on here, as well as the global warming potential. So the GWP and the TPE. You can see that the twisted steel micro reinforcement has about 2 kilograms per kilogram of CO2. So it's definitely a bit higher, but that makes sense because compared to rebar, rebar is just hot rolled. Twisted steel micro reinforcement is it's actually made from hard drawn, so it's cold work steel. That it starts with hot rolled rod, and then it's drawn out by stretching it to a smaller diameter, and then it has to be twisted as well. So it makes more sense because a lot more energy goes into that process. The good news is that Helix is twisted steel micro reinforcement is more efficient than rebar. So we make up for that in other ways, and I'll show you how that happens in a minute. So the actual impact actually ends up being lower than the rebar. And then we have the energy here. So this is estimated impact. So again, there is not an EPD for this, but we have this Athena Materials Institute report that's available upon request that provides the data that backs this up. So what we're now going to talk about is really baselining and estimating environmental performance. And I do also have a little bit of manufacturing background and training in the Six Sigma method of process improvement and the ISO 9000 method of process improvement. And really that starts with baselining. Where do you stand now? And that's what these EPDs and this data is really useful for. It's just starting. The first step to improve a process is just really understanding where you are. And then you can start to talk about how you can optimize. So once you've got that baseline, then you can start to think about, well, can you maybe optimize the concrete so it has lower carbon impact? And you saw the EPD for the concrete had different options, and some of them had higher impact than others. Another way is, can you get away with using plain concrete so you don't have to add that reinforcement to it, which has a fairly high impact? Using stronger concretes maybe allows you to use thinner materials. One thing that Something like twisted steel micro reinforcement can do is increase that flexural strength, which makes it stronger without the need for more cement, for example, which can make the concrete thinner. So you have a double impact. Alternate materials can also reduce some of the other impacts of construction as well, and add fatigue resistance to the concrete. So if you can make the concrete last even longer, for example. So really what we want to do is be smart about how we use our concrete, but it all starts with baselining it and then working on improving it. So in order to baseline it, these EPDs are useful, but we have to combine the data from the EPDs into something that represents the reinforced concrete system. And then, you can take it a step further and sum that into the entire building. But what we're going to do is just talk about how you can quantify using these EPDs, conventional reinforced concrete sections, as well as twisted steel micro reinforced sections that might only have twisted steel micro reinforcement, but may also have traditional rebar in them. So in order to do that, we have to take the EPD data from these products, or in the case of TSMR, the available, the Athena report. And we have to first quantify the amount of rebar or TSMR that's in, say, a certain volume of concrete that, or for example, if it's a slab, we can calculate how big the slab is and then how many cubic yards of concrete go in it. We have to total up the amount of steel that's in that assembly, the amount of concrete, and the amount of twisted steel micro reinforcement. And then we can just essentially cross multiply it, those values by those EPD quantities I showed you, and get an estimate for the total environmental impact. And then we can then compare, for example, a section that's conventional to one that's designed with TSMR. We can also then look at fatigue and life cycle. And one way to assess life cycle would be to relate it to fatigue. ACI has formulas that give you the amount of fatigue life increase based on the strength, the flexural strength of concrete, for example, for slabs. And you can incorporate that in essence, that becomes a multiplier, because if you can say that something is going to last twice as long, your overall impact over the life cycle of that structure is essentially half. So again, this is really for estimating purposes. You got to keep that in mind. This cannot necessarily be used for official documentation. So we have a system in-house. It's a calculator like this that allows you to put your conventional reinforced section on one side, and then the twisted steel micro reinforcement section on the other side. And it allows you to look at both the economics as well as the environmental impact. And we focus on just the global warming potential and total primary energy consumption. So you can see it calculates it here based on that Athena data. And then it also calculates the twisted steel micro reinforcement quantities. And then it compares the impact. It'll take into account thickness reductions if you have them and things like that. So if you'd like assistance with that, you can reach out to us afterwards, and we can help with that. But you can put together just a simple Excel calculator that does that cross multiplication and provides this comparison on your own. There are online calculators. We have one on our website that will do a simple comparison. Again, it's unofficial, it's an estimate. But if you want something that's actually official, that actually is backed by EPDs and LCAs for all the materials that are in the libraries, you can go to the Athena Building Materials Institute, and they actually have software that uses accredited LCAs and EPDs to actually put an assembly of an entire building together if somebody asks you to do that, and quantify the environmental impact of the building from the ground up. So that's kind of a bigger project, but I definitely would encourage you to investigate that if somebody's asked you to look into that. If you're just looking to baseline and evaluate different options, doing a a spreadsheet like this, or using a simple online calculator like this, really will allow you to kind of compare between different options of how you might build something. And that's important to note. You know, these comparative calculators are really for that type, just making those sort of high level decisions. These things like Athena are for more like producing, you know, those third party type reports for an entire building system. And you really need to kind of look at the contracts, and we'll finish up with that and what's required. So just as an example, this is a project that was done with twisted steel micro reinforcement, where 2 layers of number 5 bars were replaced with 27 pounds of the twisted steel micro reinforcement. If we use that spreadsheet based calculator and we ignore fatigue in that 700,000 square foot slab, we saved about 500,000 kilograms of CO2 by eliminating that rebar and using the twisted steel micro reinforcement. Again, the TSMR it's more efficient, so it doesn't have as high of a carbon impact. If we include fatigue, that number goes up because we're increasing that modulus of rupture of the concrete, which increases the fatigue resistance and increases the life of the concrete. So that's just an example of how you can use a comparison calculator like this. As of right now, you will see EPD mandates and requirements most likely in DOT or federal projects and things like that. California is one area where they're requiring EPDs for certain DOT projects in the contracts. So I think you'll see more and more material suppliers and vendors seeking to get EPDs on their products, or at least have data available to support it. Certainly, it's an incentive at this point for the LEED framework, but not a mandatory requirement. That may change at some point. And then, you know, I think we will probably over the next decade or so move to, you know, there'll probably be a whole industry that's created around quantifying this and consulting around how engineers can minimize the carbon impact or the environmental impact of their buildings. And this data is really important for that. So definitely need to keep an open mind to this and keep your eyes open, because you don't want to be blindsided if you see a requirement for this and you don't really have the background or the information that's needed to understand it. So that was kind of the point of this presentation. So just wrapping up, you know, global warming is caused by human-mediated input of materials into the atmosphere, which trap the radiation exiting into space. So, you know, the result of that is gradual heating over long periods of time. So we definitely can measure that CO2, and we can look at global temperatures, and we're seeing trends up in both of those. Concrete is one of the most widely used environmental materials, and because it's one of the most widely used material, it does produce a lot of CO2, and that's really the main purpose, or main reason. Use of things like PCRs, LPDs, and other things like EIAs and EAs that we didn't really talk about, environmental audits, can assess the impact of materials, first to baseline them and then to improve them. And that was again part of the point of this presentation, is to provide some basic understanding of those things. We discussed common construction materials that have different impacts, and how we can use those to kind of optimize global warming impact by doing things like optimizing the design, maybe making the concrete thinner, looking at alternate concrete materials to reduce the impact of the mix. There's even things where you can re-inject CO2 into the concrete that kind of are outside the scope of this presentation that have been discussed. Strengthening the material, and very importantly, increasing its lifespan. Let's not focus just on the initial carbon, but let's look at, how can we build buildings that last 1,000 years rather than just 100 years or 60 years, And concrete is really the only material that offers us a really good alternative way, or a good way to do that. And then let's look at alternate reinforcement techniques that might optimize things further. We did talk about TSMR and how that may be a part of it. It certainly isn't an overall solution to this issue of environmental impact, but it definitely can have some impact, at least in terms of reducing some of the impact from the reinforcement. And we reviewed an example of a project with that ABB, that slab with the 2 layers of number 5, and just demonstrated how you could assess that. So, just wrapping back to our learning objectives, hopefully you've taken away from this presentation a good set of knowledge in terms of how to understand and communicate these things, identify and assess those metrics that affect global warming, and then most importantly, be able to communicate and describe and critique things in such a way that people understand the impact of how you're designing, but also gives you a framework to start to improve and think critically about how you can do better, not just on your project, but just from a global perspective. So thank you very much for your participation. I really appreciate your attention. There was a lot of material covered here. Again, on behalf of my our company Helix Steel, if there are any questions that you have, all of our engineering team are familiar with these approaches and the calculator that I presented, and are happy to answer your questions. So with that, thank you, and really appreciate your attendance today.